Alright, for our final problem, looking at fluids, we're going to deal with a much harder problem, but something that is well within the rights of something that we should be able to solve. This time, what I've got is I've got a setup of a cylinder, very poorly drawn, but that's fine, that has a height here of 0.7 meters. And this cylinder is filled with water up to the 0.7 meter mark. It's on a little stand that puts it 0.3 meters. Let me connect these so that we've got a better idea. And we've got a little tray down here that is going to collect some water, because what we're going to do is have a hole right here, and water is going to be falling out of it down into a little cup. We've got a supply of water up here that's going to keep this water level right at 0.7 meters, just to keep things in a steady state situation. Now there are a couple of things that I want to know about this. First thing I'm going to tell you is the, let me see what I've got. The radius of our hole that the water's falling through is 0.0010 meters. In other words, about 1 millimeter. Okay. The first thing I want to find is the velocity of the water right there. Okay. So how we're going to approach this is we're going to use the Bernoulli equation. So, we've got water up here at point number 1. We can call that 1. Down here at point number 2. And in fact, what I'll do is grab some more colors. And we'll do this way. Point 1 and point 2. Okay? So, in both cases, using Bernoulli, we'll have pressure plus 1/2 rho v squared plus rho gh is going to be equal to the same values at another location. Pressure plus 1/2 rho v squared, where v is velocity, plus rho gh. Well, the first things I'm going to point out are our pressures are actually going to cancel out. In this case, both of these are open to the atmosphere, and so our pressures are just atmospheric pressure. We'll have the same thing over here and here, so that's 101,325, but I've got it on both sides of the equation, so I could just subtract it over and they're going to disappear. They're going to fall out, which is good. Okay? Up here, at point 1, well, the water's pretty much not moving at all. It's just kind of the surface there. So since its velocity up here equals 0, that means that this guy also goes to 0. And by the same token, because I'm going to set my height equal to 0, at least for now, right here, y equals 0, that means that down here, at point 2, our height's going to be 0, and that goes away. You'll see that this looks a lot like the energy balances that we did before when we studied conservation of energy. We'll end up with rho gh, so potential energy that we have from up here. In this case, it's a little modified because what's actually happening is this is keeping track of the force of water, the energy associated with water pushing down here, that's going to then be translated into a water pressure that pushes this water at the bottom out, 1/2 rho v squared. Alright, well, we see that we've got a rho on both sides, that cancels out, and if I do some quick algebra here, I can find that my velocity is going to be equal to the square root of 2gh. Hopefully, that's looking familiar to you. That's one of those general solutions when we were dealing with energy, and so it's a good one to have around. Well, if I have 2 times 9.81 meters per second squared times my h, which in this case is 0.7 meters, I'm going to find that the velocity that the water is coming out here at point number 2 is going to be equal to 3.7 meters per second. And so that's the first thing that I'm looking for. The second thing I'm looking for, B. What's my flow rate? How much water do I have going through there at a given point? Well, if you remember from our equations, our flow rate is equal to our area times our velocity. We just found our velocity here. And so now we just need our area. Area is going to be equal to pi r squared. Our little hole's probably pretty circular, where r is going to be equal to that guy there, 1 centimeter. When I plug these values in, I find that my flow rate is going to be 1.16 times 10 to the negative fifth cubic meters per second. Okay, so that's the next thing that we wanted. And then finally, with this flow rate, I want to know how much water is collected in this dish down here. If I let the clock tick for 2 minutes. Okay, so we want a volume of water collected in 2 minutes. Well, we've got our flow rate. We know how much volume is going in there for every second. So if I take my volume, which is, well, let me phrase this a different way. We'll do this more logically. We have our flow rate, Q, which is nothing more than our volume per unit time, right? Well, if I multiply both sides by time, I can find my volume simply by taking my flow rate times the time. So I've got my flow rate times time. Well, my flow rate is 1.16 times 10 to the negative fifth cubic meters per second. Now I'm going to multiply that by my time, which is 2 minutes. I'm also going to need a factor of 60 seconds per 1 minute over here to convert the 2 minutes into seconds so that my seconds will cancel out. I want all of my units gone except for cubic meters. So I have a volume of water in that dish. And solving for that, I find that it is 0.0140 cubic meters, which comes up to, off the top of my head, that looks like something like 1.4 liters. So, that's not a small amount of water. Okay, so we have gone through and we have found multiple different things for this one problem. This is the sort of thing that might be asked on a major exam or the AP exam. So, but we can see that we started off and applied the Bernoulli equation so that we could get an idea of the velocity here, and with the velocities we can find out flow rates, and with flow rates we can find out how quickly something is draining or filling, and we can do lots of stuff. So